Good morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Apptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source. Hello. Still dancing, huh?
I'm still dancing. It's that music. It's that intro music, man. I just feel like it's like 1999 and I'm just, I don't know, 20 again.
It is catchy. It's catchy.
Awesome. Hey, Zane. Good afternoon.
Good afternoon. How are you?
I am very excited to be here. Two of my favorite people, of course, other than you, are going to be joining us today to be talking about one of the most popular topics that, well, I mean, all of them are kind of popular, but the most popular topic that we get at CIQ and questions that we get are about containers, right? It's like a revolution, right? Like when we kind of figured out that we could do this, it was like, yes, we need this. And specifically Apptainer is more for HPC, and we're going to talk about that. But I am very excited to get into our container education series right now.
Back into it.
Boom, 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 boom. All right, should we bring on our guys? There we go.
I was gonna say, I hope they're here.
I know.
That would be kind of funny.
You, Zane.
If it was just been you and me, it could have been a much more interesting conversation about, could read stuff.
I actually did bring up Dave Godlove's article that I think they're going to reference, put into the chat there. It is a blog on our website, and it's thorough, right? I mean, these guys are really good at what they do. They document everything. They make videos of everything. They are happy to share all of the knowledge. So thank you, Dave Godlove, for that amazing blog. And I think most people know you, but would you like to introduce yourself?
I will introduce myself. You might hear a bunch of wacky, weird background noise today. I'm in a different location than normal, so just roll with it. Rose, you're too kind. Thank you so much. You always make me feel humble with all your praise. Yeah. So I will introduce myself for the probably a zillion people who don't know me. I'm Dave Godlove. I used to be a research scientist. I used to work at the NIH for a while, and as a scientist, I became interested in high performance computing, and I got on with the container revolution while I was there, and started working with Greg and some other people helping to develop Apptainer, and now I'm here to talk about it as a solutions architect. So cool.
Yeah. It is cool, man. And thank you all for all your good work. So if you guys are in the Apptainer Slack community and you ask a question, I mean, I would not be surprised if Dave Godlove is the first one to answer you. He is on top of it, and he's been doing this for a long, long time. So, and he's been all over the place. He's seen all kinds of craziness of what it can and cannot do, and is happy to help you. So we definitely support you in engaging in that community and getting all your questions answered.
And if you're reading the documentation, Dave probably wrote it.
That is accurate. So if there's an issue with the documentation
right now, just
now you know how to find him. Ping him in the Slack community and be like,
yes.
Dave, this. I actually have not found that at all. I haven't heard anybody come back and be like, this is inaccurate. You're on it, man. So thank you.
I will say, if you actually literally do want to track me down, and you made me think of this because I just put this in Slack. If you're in the Bay Area and you want to track me down, Monday at 4 p.m. on the Stanford campus, I dropped a link in Slack to the actual location and stuff. We're going to be giving almost a 2-hour workshop, and it's going to be hopefully kind of audience driven. So if you have questions, if you have things you want to talk about, come on down and we'll talk about it.
And that is open to the public, right, Dave? If I saw that correctly.
Yeah, that's open to anybody. It's on
Excellent.
It's on the Stanford campus, but anybody can come. And I just got news that's hard to hear me. Hopefully,
just yell.
I'll just yell. Okay, yeah. Sorry.
Yell over the heavy equipment behind you.
Yeah, you can tell.
Look at him. He's so irritated by it, but he won't actually say he's irritated by it.
about? I gotta get you one of these microphones, man, so you can like get right up in it. And yeah, there we go. All right. You know what,
Jonathan knows.
Alex?
Jonathan's got it.
Send him something. All right, cool. Yeah, Jonathan, hi, welcome. Would you like to introduce yourself?
Yes, thanks, Rose. My name's Jonathan Anderson, and I'm a solutions architect as well here at CIQ. And I haven't been involved in the development of Apptainer or Singularity before it as long as Dave has for sure. But I was using it at a university site in a pretty typical HPC use case in the past, and am glad to be on the kind of support and development and benchmarking and all experimental, interesting things with Apptainer front here within CIQ. In fact, just before this, I almost missed our queue to jump online and do this webinar because I was busy running a huge matrix of benchmarks that maybe we'll get into later as we get to the end of the implications of what we're going to be talking about today.
Jonathan, you know that I kind of slid in at the end too, but I would have been chasing you down. Don't worry. I would not have let you go too far.
Come on in. We need you.
Exactly.
Awesome. Okay, Zane. So where are we going with this? We are going to be starting, in case we did introductions. That is amazing. And we're going to be talking about MPI with Apptainer. And there's a couple of little kinks that kind of get in the way. And we're containerizing MPI. And what does that mean? And how does that work with other things?
I think we should take one step back and just for the people who don't know what MPI is.
Google
if Dave or Jonathan, that would involve me having to read something, and it's much better when Jonathan and Dave explain things to me. I'm more of an auditory learner myself.
Totally.
Yeah, maybe I'll start with the MPI introduction. So MPI is probably I shouldn't even say probably. It's the most common practice in traditional HPC for bringing multiple nodes together and having them work in concert on a single problem. So MPI stands for Message Passing Interface, and it's a set of standards for writing your application in such a way that it is given a list of contacts for other nodes, other computers that are participating in an application, in a computation or a calculation, that kind of thing, and dividing that work up so that each node, each computer in your job is doing a different part of the work. And then MPI gives you the verbs, the actions necessary to pass information between those. And there are some simple like point-to-point messages where one node, one part of the computation can send or receive messages with another. And then on the back of that are collective operations for having all of the nodes share information to all of the other nodes, or collective operations that reduce all of the nodes down to one result that is received by one node, that kind of thing. And so there are a number of implementations. Some of the more popular open source implementations are MPitch, OpenMPI, and MVPitch. But then there are proprietary implementations, usually forks from one of these open source implementations as well. So like Intel has one, IBM has one, that are kind of built and supported to run in specific hardware environments. But it's pretty typical for, at least in the university space, to have one or more of these open source MPI implementations on your system.
So it's really not as much of a... They all pretty much do the same thing. If you write your code, do you have to write it differently for every one of them? If one's a fork of the other, it's probably really similar. But if it's one of the proprietary ones, are they similar?
Yeah, so they should adhere to the standard, the specification. And in general, what you'll see is most applications can be compiled against any of the common MPI implementations. That's not necessarily the case, though, and most applications will have one that their developers tested against. And so often you care about which MPI you're going to run your application with, because it might perform differently or better with different implementations of MPI, even if it runs on them at all. And it's not unusual for it to be able to run with any of the MPI implementations, but it's also not unusual for it to have a preferred highest performing one. But then that also is a compile time concern. The MPI implementation that you're building against has to be built once against that, and now you have this compiled binary that only works with that MPI. and you can't just mix and match it to all of the others. So this is why lots of HPC sites will not only have all of the MPIs available, but also will have the MPIs compiled in different ways depending on how you might want to compile your downstream application, what compiler you're going to compile it against, or what math libraries, that kind of thing.
I can only imagine in containers that can cause issues.
Well, it's one of the problems that containers is meant to help solve. So when you do this in one big namespace, what's typical is you have like a file system that's /software or /opt or something like that, where you compile all of this software in one place that's shared to all of your compute nodes. But when you start having to worry about the matrix of possible different combinations of all of these things together, you're trying to build an environment that has all of the possible permutations of all of the software that you might care about. And it gets very hairy and very big and complex very fast, especially when you need to upgrade something. Now you have this huge dependency chain of things you have to update. One of the goals of containers is to be able to say, we don't care about all of the possibilities. We just care about what this one application needs. And we want to be able to pack the libraries and the MPI implementation that application needs with that application, so it's one thing. And you don't have to worry about all of the other possibilities that might be applicable on the system. Those can be in different containers and not have to be in one big shared namespace.
Yeah, I guess that's another topic as well, is being able to string containers together. So that's very cool. So I have to say, you said /opt. I feel like last time I said that I was putting stuff in /opt, somebody laughed at me and told me I was old school. Is that normal now? People don't put stuff in opt anymore?
We do old school things in traditional HPC all the time.
That's what I thought. I thought that's where everything went. Optional.
Stuff should go in opt. Who told
Thank
you
you.
that, Wayne?
I'm a big fan of opt.
Yeah.
Okay, I'm just making sure I wasn't alone here. I thought it was a little odd that I was being laughed at for using /opt still.
Don't get me started, man.
Okay.
Spreading out all the configuration files and binaries and stuff all over all the different directories. Who thought of that? Who came up with that nonsense?
Not me, man. Not me.
/opt is the ancestor of containers in my mind.
There you go.
That's a good point.
No wonder I feel kinship with it.
I like that. So, Dave, you wrote a blog. It's about Apptainer and MPI. Tell us about it.
Cool. Yeah. Well,
Don't read it to us. Just tell us about it.
well, I wrote the. Oh yeah.
If you didn't come, Rose and I were going to take turns reading paragraph by paragraph, but it's much better if you just tell
I
the
have it
story.
open.
Why did we show up, Dave? That would have been so great.
No, it would have been so awful.
Reading in the round. with Zane and
Before I go into that blog post and talking about that, I just want to acknowledge that Zane and me are basically sitting across from each other in the same room, right? I mean, really, our backgrounds, it looks like.
That's kind of what it looks like. I agree.
Wow. Okay. Yeah, I just want to acknowledge that. We're really not. We're like, totally different parts of the country. But okay. So I want to preface all this by saying that it's me and Jonathan tag teaming this, because even though I wrote this blog post, most of the stuff that's in it was Jonathan's work. And he and I have been both kind of, we feel like we've given this webinar before, even though we haven't, because we've both gone to a bunch of different meetings, but they've all been, kind of like different fragmented groups. And we've talked about this in a lot of different settings at this point in time, but we haven't actually done the webinar on it, which is kind of an oversight. But I think that, so Jonathan, you will have to kind of like keep me honest as far as the background on this goes. But I think Jonathan started to investigate like MPI within containers, and like there have been for a long time sort of several different like models, or several different ways in which we suggest that you run MPI inside containers. There's like a fully containerized approach, which is easy because it's only one node. So if you want to use MPI basically to spread your process across multiple CPUs within a single node, you can totally do that. And you can do that by sticking all of your MPI implementation inside the container, and then just running it. But then things become a little harder when you try to reach out and go across nodes. And I want to say, like, in the blog post that we keep referencing, that hopefully we'll get some links and stuff too, I really lay out like one problem, But I actually think, and maybe we can talk a little bit more about it today, that there's actually two big problems with MPI inside the container. And that blog post really only kind of talks about one of them. So let me kind of lay those problems out and kind of talk about, what they are. And then we'll kind of go through and talk about, how people have traditionally solved them, and then the new way that we're advocating that people start to look at solving this problem. So when you first start an MPI application, so what you do is you write your code to be MPI aware, and then you compile it against a certain set of MPI libraries. And then you have that set of MPI, or that implementation of MPI, available to you on your HPC system. And what you do in order to launch it and make everything happen is, from one particular node, you say, okay, MPI exec my process. And what that does is MPI says, ooh, okay, you want me to go out to all these nodes and find that process that you just told me to start, and start it either, just one on all the nodes or multiple implementations on all the nodes, whichever you've kind of set up. And then you want me to assign each one of them a rank and basically tell them how to talk to each other. And that first initial step is commonly referred to as the wire up of the job. So if you just do that on bare metal, like I just suggested, it works fine. MPI, lives on the node where you started the job, and it also lives everywhere else on all the other nodes, and so it can fan out and work everywhere it needs to work, and assign everybody rank, and do all the stuff it needs to do, and everything's just happy. And that process, yeah, there you go. That process lives on all the nodes as well, and that's kind of like the big key here, is that the process that you've told MPI exec to go out and find, it can go find it. It's fine because it lives on shared storage or something, and it just goes and finds it and starts it. Now the problem when you try to do this from within a container is, now you're inside this little container, on the node, and you say, okay, MPI exec this process, and MPI says, yes sir, yes ma'am, I'm going to run out and do this. And it uses SSH or RSH or whatever to go out to all the other nodes. And then, but when it does that, it pops out of the container, and that's kind of the key thing. And then it looks around and says, where's that process that I was supposed to start? And the process is stuck inside the container. So MPI exec can't see it anymore. So then MPI exec just reports back and says, I don't know, you told me to do something I can't do. Here's a bunch of errors that you'll never figure out what they mean, blah. And then that's the problem. That's the first problem. Okay, that's the first problem. The second problem is, for MPI to be performant, which, if we're dealing with high performance computing, we want applications to be performant. Mm-hmm. So for MPI to be performant, it has to have really, really high speed interconnects in between the nodes. Usually just plain old Ethernet's not going to do it. Usually you need to have some sort of InfiniBand or OmniPath or some really high speed fabric between your nodes for them to talk to each other. This problem ends up being kind of similar to the way that that GPUs work, in that you've got drivers for the actual hardware for this fabric, and those drivers, they have two components. They've got a component which is tied to the kernel, which is a kernel module, and they've got another component which is the user libraries that are supposed to interact with that kernel module, and you got to match them up. And the problem is, you get the kernel into your container at runtime, just like, because that's the way container works, and so you get that kernel module and you don't control what you get. But the libraries, you have to match those up. You do control what those are, and those have to match the kernel module. And then that gets complicated, because depending on how you've compiled your application, you might have compiled it directly against those libraries. So it might be like, well, I really need to have version 10 of these libraries, but my kernel is running version 9 of the module, and so basically my whole container now won't work with this. And so then things become not portable, and so those are the two big problems: the wire up problem, and then the high speed interconnect problem. Those are the two kind of big issues that we're trying to address now. And the first of those is the one that this blog post really deals with, is the wire up problem. But we also have some ideas about the high speed fabric, and I think it'd be cool to talk about those a little bit today too.
So Dave, 10 gigabit, if people are building kind of the smaller environments and they're doing their own thing on copper, is 10 gigabit okay?
I mean,
Not ideal, but okay.
yeah. So I don't even know what the current state of the art is as far as high speed fabrics. What is it, about 100 gigabit?
I feel like I saw somewhere that there was a 200 gigabit.
Yeah, 100 gigabit is about 5 years old now.
So it's not even state of the art anymore.
Yeah.
Cutting edge is like what?
I think 400 and 800 is coming out.
Crazy
Yeah,
fast.
10. And then it's very application dependent too, right? I mean,
Makes sense.
Yeah, it's like how much essentially how much message passing is your application doing?
Yeah.
You know.
Makes sense.
Wow, Dave.
Sorry to cut you off, Dave.
Yeah, no, I feel like you need to take a breath or something. Those feel like big problems. And
Yeah, well,
so,
they're
yeah.
interesting. They're big and interesting problems.
But you've solved them?
No, Jonathan has solved them.
We've been making moves that we think simplifies this, and particularly in containerized workloads. So we're going to show a bit of that, and I don't know, Dave. I don't want to skip over like your flow. What comes next? What are we talking about next?
Well, I guess next we should kind of summarize the ways in which people have suggested that this problem should be solved, and then just kind of maybe provide some examples of that and like show what that looks like and why it kind of sucks. I think that would be the best thing to do. Um, so, okay, going back to the wire up problem. You'll recall. So the problem is that you fire off MPI exec, it runs out to all these other nodes. It's outside the container, and it says I can't do what you asked me to do. I can't find the process that you want me to start on all these other nodes. So what if you called MPI exec outside the container, and you said the process that I want you to run is Apptainer, and I want you to run Apptainer with these arguments, so that you start up a container and then you execute a process from within the container. So that should work. And so what ends up happening then is that MPI is on the host system. You give it an Apptainer command to MPI exec. It runs out to all the other nodes. It finds Apptainer. It finds your container. All that stuff is on the host system, on the host file system, and it starts everything up. But the problem is, it also needs to be inside the container to handle doing things like assigning rank and setting up the communication and just all the stuff that MPI does and the actual running of the program and everything. So you need it, if you're going to do that, you need it outside the container and inside the container both. And then not only do you need like some MPI outside the container and some MPI inside the container, but even though there's like standards and stuff, it turns out that MPI flavors and versions don't like one another at all. So if you start MPI on the host system and it's a different version than what's inside the container, it's almost always going to freak out and say, I don't know, I'm having an identity crisis. I can't work with this, and it's not going to run. Or if it does run, it's going to be not very performant or whatever. So then you're in this state of trying to match the exact version of MPI, which is on the host, with the exact version of MPI that you've got installed inside the container. And not just the exact like flavor and the exact version, but even the way in which you've compiled it can matter, to make sure that the two work together properly. So that's kind of like, what you're running up against. But that's the way that people have suggested that you should do it. That's kind of like the standard way that we've been doing it for a while. And if you're gonna have MPI on the host and MPI inside the container, there's like two different methods that people advocate for doing this. One is that you actually install the entire MPI implementation inside the container. You just match it to the one on the host, and this is commonly referred to as the hybrid model. It's kind of hybrid because it's the host MPI and the containerized MPI are working in tandem together. And then there's a bind model where you basically use the bind mount architecture of Apptainer to take everything, all the MPI libraries and everything that are on the host, and you bind mount them into the container at runtime. So the hybrid model and the bind model are the two kind of like historical ways in which this problem has been solved.
So do we do have a comment, David? I think it applies. Shinlong, thank you for the comment.
Yeah.
I also want to
somebody's already doing it the right way.
I also want to point out Justin and Dave agreed on the op. So sorry, go back to Apptainer.
So it says we use srun to launch Singularity, no MPI on the host. Bind the IB libraries from the host to the containers. It works well. So yeah, this is going to be kind of like the third model, but there's going to be some there's a little bit of some variation on that. So this is to kind of do look ahead at what we're going to be talking about towards the end after we show the other two methods. There's this new-ish technology standard, not really that new, but it's called PMI. And PMI is a standard basically for doing that wire up that I was talking about. And so if you compile a tool like Slurm, which is what srun comes from, to use PMI, and then you've got the same PMI implementation inside your container, then all this like matching MPI garbage kind of goes away, and you don't have to worry about that anymore. Now the bind the IB libraries from the host container, I think that we're going to be talking about a way in which you might be able to do even a little bit better than that through something called libfabric that we've been looking at. But I'll let Jonathan talk more about that when the time is right. I don't know. I could kind of talk about the older school approaches a little bit more and kind of like go through some demos and show how those are done. Is that good now, or Jonathan, do you have something else that you'd like to add at this point?
I don't have anything else to add. And yeah, we can do that. Like Dave's been having trouble with screen share, so I think that's still going on, right? So I was gonna.
Well, let me try, because what I did is I installed the SSH client for Chrome, and I think I should be able to share my browser if I can't share anything else. For some reason, it seems like it's trying to allow me to share my browser. So I'll try that, and you guys can tell me if you can see that or not.
We got it.
Okay, you're running an SSH client as a browser extension?
Man.
This is horrifying to me.
I have a great story about this, Jonathan, at some point. Not about this one in particular, but I don't know if you were ever dealing with Solaris, but Sun, as a troubleshooting tool, used to have an SSH tool that you could go to a Solaris or a Sun website and actually get a console up. You could share the URL so the Sun admin from Sun helping you could actually see it too. It was handy and terrifying.
Yeah. We could, we should do a webinar on why this is horrifying. I think it's like a totally okay idea. So anyhow, I don't know. So I'm having trouble. Previously, I had a kind of an epic fail during one of these webinars where I really could not screen share. And it turned out that I had updated my system and it was running Wayland instead of X11 for graphics. And because of that, it wouldn't share. I'm running X11 now. I have no idea why it won't share. Won't share anything except for browsers. So
I think we're going to go back and put an actual link directly to that part of the webinar where you had to switch to a monitor on camera and turn it around. That was fantastic.
It was the best. He was like, "Can you see it, guys? Can you see it?"
Yeah. That was a day. All right. So anyhow, so the model that I was talking about, where you actually install the MPI implementation into the container itself, and you actually have it on the host too. That's called the hybrid model here. And so let me go ahead and show you. I've got my own implementation of MPI that I've installed here in my home directory, because we don't have a version of MPI that is running system wide on the system. So I got to export some environment variables just to make that available. And so let me go ahead now that I've got that exported, and I'll go into this hybrid directory, and I'll kind of just give you a sense of what's going on here. So, as I just said, I installed MPI. So I know exactly how this MPI was installed. I'm like the administrator of this particular MPI. I know how it was installed and all that kind of stuff. Even so, even with all the knowledge that I have of how this MPI was installed, I found it very difficult to install a matching version of MPI that was also compiled in exactly the same way into my container. And so let me give you a sense of that. So first off, I'm going to be running this little hello world.c program. And let me just give you a little heads up of what this looks like. So this is a pretty short program that was originally written by Wes Kendall and that Jonathan modified. And what it does, it just sets up however many MPI ranks on however many nodes you ask it to, and then it just gives you some messages. It just prints to you, what rank it is, what host it's running on, what CPU it's running on, and some other information as well.
No cows though.
No cows today, unfortunately. Man, we should redo this so that it's like an LOL cow MPI. So that's the program that I want to containerize and run. So to do that, I have to install MPI inside the container. I also have to get that C file inside the container, and then I have to compile it against the MPI that I installed inside the container. All right, so here we go. So this is the definition file that I ultimately came up with. So I started this definition file from like an example that's up on the Apptainer documentation page, and then I just sort of edited the definition file until I got what I needed out of it. And as I go through this thing, you can see it became pretty complicated. One of the reasons it became complicated is because the MPI that I've got on the host system, it is compiled against a bunch of libraries, which we do have installed centrally, which we have installed here with OpenHPC. And so in order to kind of get everything to work properly inside the container, I also had to install some of the same libraries inside and some of the same applications inside of the container so that I could then compile my OpenMPI against those same libraries. And so then here at the very bottom, I'm just cding to opt, that's directory, and just running MPI-cc, this is the thing that's actually going to compile that MPI Hello World C program into an actual executable. This is pretty complicated. It took me a while to get this right. Okay. And, so I can't see you guys too while I'm screen sharing. So if you're like doing like this or something, I won't see it. So if you want,
I'll yell at you, Dave.
Yeah, just holler at me and I'll stop. All right.
You have a question whenever you're ready for a question, though.
Okay. Yeah. So I've just showed you the definition file. This is the built container here, and the next thing I'm going to show you is how to run the job. But I'll pause for a question.
It's from Mr. DeBonis. Appreciate it. Are there performance impacts using MPI versus bind?
PMI.
PMI.
I'm sorry.
Yeah.
I know. That was confusing to me too. I mean, you could have named it something else, right? MPI, PMI, all the acronyms.
It's too many letters.
PSM. It is complicated.
So you got this, Dave? Are there performance impacts using PMI versus bind?
So here's what we're going to do. I think that I'm going to let Jonathan field the MPI specific questions, and I'm going to field the container specific questions. How's that
cool
sound?
So PMI here shouldn't in itself really shouldn't introduce any performance impact, or if it does, the performance impact would be on initialization. PMI is just used for starting processes on the node. Once they're running, they're the same processes that would have been running before anyway. So there are even more modern than the PMI that we're using right now. Work happening in PMI called PMI-X. It's the PMI work for exascale. For systems where the scalability of the system meant that process startup was taking so long that it just wasn't tenable anymore. So that is an issue. that we intend with this work to further address by moving to PMI-X, but that's a work in progress still for us, and our ability to use it in this containerized environment. But there are other performance implications that are unrelated to PMI that we're investigating right now. Like I mentioned, we're running benchmarks and things like that to understand what that is, and then once we see where there might be performance issues, dig into that with development.
Just as another little wrinkle to add to all this too, people should be aware that so PMI is a standard, but like with all good standards, there's a lot of different versions of the standard. So there's PMI 1, there's PMI 2, and there's PMI X, and there are multiple versions within PMI X. So it's still, there's still stuff that you have to match up and be aware of, but it's a little bit easier than all the universe of different MPIs that you could have, different versions and flavors and so on.
Does it have to be compiled code, Dave? Can you just have a compiled library and call it from something like Python, non-compiled? Or does it even matter?
Does what have to be compiled? The MPI-enabled application?
Everything you're doing here is all C code, right? It's compiled code. What if I had just a Python program?
I think that there are I should back up and I should say, and like, I'm not a super huge expert in MPI. And this is because most of what I did at the NIH was like high throughput computing. So big parallel jobs, well, parallel groups of jobs. But I think that there are like parallel libraries for Python. I'm not really sure how they work though.
Yeah, there are MPI implementations for Python, and they ultimately wrap a C implementation.
Okay.
So you build that Python extension against an MPI implementation. MPI itself is ultimately almost always, if not always, implemented as a C, C++, and Fortran library that you build your code against. So you can compile a Python interface for a given MPI implementation and then write Python code that uses MPI. It's not super common, but it is a thing that people do. But most MPI code is either C or Fortran.
Sure, people want it to be fast and efficient. I get it, but as much Python as we see out there nowadays,
or there's scientists and mathematicians that just do everything in Fortran, and I don't know Fortran, but that's what people do.
ChatGPT.
I'm going to show everybody now my job.sh, which I wrote myself. I did not use ChatGPT for this.
Thank you.
So this is the submission script that I'm going to use to send this off through Slurm. And so it's got these SBatch directives. Really what we're interested in today is that we're going to run just two different processes, and the tasks per node is going to be one. So I'm going to use two different nodes, one task per node. Since I'm using libfabric, I can go ahead and set this environment variable, and it's going to give me some more information about what's actually happening and what's the interconnect that's being used. And then I'm just going to do an MPI run, and I'm going to go ahead and do an Apptainer exec. So once again, with this hybrid model, you execute the MPI run, and then you give it an Apptainer command. And then once you've got that Apptainer command, you go ahead and give it. So this is going to execute the following command. So this command inside this container. I don't know why I'm highlighting MPI hello world everywhere. All right, so yeah, that's the way that I clear whenever I'm highlighting something. Okay, so I'm going to go ahead and submit that with SBatch. And this is going to give us the moment of truth to see if I actually forgot anything or if this is going to work. Job number 599. Let's go ahead and see. It should run pretty quick. All the stuff. It worked, as we can see here. So all the other stuff is just information that libfabric is giving me about what it finds, what it doesn't find, what it opens, how it feels. But we can see there. Here's another three-letter abbreviation for you guys, PSM. So if we can see that it used PSM2, which is not PMI, is actually the fabric adapter for OmniPath. So not only did it run, but it ran using the high-speed interconnect, the OmniPath fabric adapter. And then down here we see, we ran on compute node 5 and compute node 6. So two different nodes, two different ranks, same CPU, two different mount namespaces because it's two different containers. Although it could be the same mount namespace because it's on two different nodes, but it wasn't. Cool. So that's the hybrid model. Now let's talk about why the hybrid model sucks. So I already kind of alluded to the fact that this was a big pain for me to build this container. That was a complicated definition file. It probably ended up with some garbage in it that it didn't need to have in it just because I was doing trial and error and trying to figure out how to make it work. And once it did work, I didn't want to mess with it anymore. But just that wasted time, that's not the whole story, because if I take this this container now that I've built anywhere else and I try to run it again, unless I have exactly the same OpenMPI compiled in a very, very similar way, it's not going to work anymore. So that's one of the main advantages of having containers, right? Is, you can take a container and throw it up on Docker Hub. Somebody else can grab it and run it. You can grab it in the future and run it somewhere else. I can't do that with this container. It's not portable anymore. And that's a huge drawback, right? And it's one of the big reasons I think that, Jonathan, you were talking about this in one of your previous presentations. It's one of the big reasons you don't see a bunch of MPI-enabled codes that already exist up in places like Docker Hub that you can pull down and just run, because they're too bespoke. They have to be compiled, more specifically for the environment where the application is actually going to run.
So, Dave, excuse me, sorry, what do you mean by it's not portable anymore? Is it because the MPI had to come out of it to run properly?
It's because I had to match really carefully. So there's multiple flavors of MPI. There's Open MPI, NPitch, MBA pitch, stuff. So I had to first off make sure I was using Open MPI because that's what I have installed on the host. But not only did I have to make sure that I was using Open MPI, but I had to match the actual version of Open MPI that I was using inside the container to what's already running on the host. And not only that, but I had to make sure that, so you can compile it in lots of different ways. You can compile it against different sets of libraries. You can omit libraries, and you basically lose out on feature sets and stuff if you compile it in different ways. But I had to make sure that the way in which I compiled it was also very similar to the way that it's compiled on the host. And so because of that, it's really matching very tightly what's on the host. And it's I'm not going to say it will not run on in another environment, but it would be pretty lucky if it did.
Thank you.
Yeah, does that make sense?
I mean, it does make sense, but I mean, I guess I don't totally understand all the details, because if you had that specific MPI on another machine or somebody else had it, I mean, they could still pull that same container and run it, right? I mean,
yeah,
so you could.
The goal for the container, though, is that there shouldn't have to be a caveat like that.
Right.
There shouldn't be, this container will run in your environment if you have all these dependencies, or at least you want to reduce the number of those dependencies and certainly reduce how specific they are. And so, Dave, if you pull up your job file again, or cat it or something, that MPI run there on the left is installed on the host. And then MPI hello world inside the container is also built against an MPI. And with those having to match, we say that the container itself is not portable to systems that have arbitrary MPIs, or what our goal is to not even need MPI, like our previous poster mentioned. You shouldn't even need the MPI on the host because it's really just an application concern.
Okay, great. Thanks for clearing that up. I think we actually have another question. Is that true, Jess? Do we want to pop that up now?
And Dave, we're kind of running out of time, so we might want to jump ahead just to the the final thing rather
I'm
than
gonna go
showing off
through.
the bind
I'm gonna go
model.
through the bind thing really, really quick just to show how awful it is, and then we can jump to the
Okay.
next thing. I won't actually run it. Oh, well, sorry. The question I was going to read it. Is it even worth using external PMI-X versus PMI-2 included in Slurm for smaller systems? We got bit by some changes with the rel and PMI-X and currently fall back to PMI-2 at the moment. Yeah, so we're using PMI-2 because the open HPC installation of Slurm that we have on this system doesn't support PMI-X or PIMX. It just supports PMI-2. And I guess there's some reasons, like maybe some security types of reasons for that I don't know all the details of. But yeah, we're using PMI-2 here. And I think that Jonathan's even finding there's some reasons even to go back and use PMI-1 or just
Yeah.
PMI.
So what I've noticed is that if you compile an application with PMI2, PMI2 appears, from what I've seen, to have some of that same MPI problem where there's a standard, but then the implementations kind of took it in all these spaces. So if you build an application, or if you build an MPI implementation against PMI2, it ends up pulling in an implementation of PMI2 to build against, which looks like by default it typically is building against Slurm inside of your container. And I didn't like the feel of that. And we hadn't tested yet whether you could build an application like that and run it on some other PMI2 supporting resource manager. I was concerned that we were losing some compatibility there. Slurm's pretty popular, but we wouldn't want to make that a requirement. So for most cases right now, I've been trying to build against PMI1, or what MVPitch calls like simple PMI, and that's still been working just fine. The reason I'm most interested in PMI-X is to get away from that resource manager dependency, so that we could be building again against a standard or an upstream implementation rather than against a specific resource manager like Slurm. Oh,
Did you? It's okay, Jess. You can put that question
yeah.
in.
Yeah, that's cool.
Like to engage with our people. Just put. Oh, it was a comment. It wasn't a question. Okay.
Kind of in response. Yeah. Okay, so just really quick. So the bind model, you'll remember, says don't install MPI inside the container. Just grab it from the host at runtime and bind mount it in. And so if we do this, what you have to do is you have to compile the MPI hello world script on the host and then copy it into the container at runtime or at build time, which is what I'm doing here with this files. This is not the MPI hello world.c anymore. It's just MPI hello world. And then the environment here is just setting the path, kind of similar to how you saw me set the path earlier, although there's some other libraries and stuff on the path here because they already exist on my path on the host. Okay, so that's a little bit simpler because you're not actually installing MPI inside the container, but there's a caveat. And here's the caveat. If you do this, you have to bind mount all of the MPI implementation on the host into the container at runtime. Okay. And then once you do that, once you bind mount that in, you actually have to start bind mounting all the libraries that it's linked to. And you have to go down this rabbit hole where you just start bind mounting all this nonsense into the container at runtime. And it ends up just being like, what you're doing is you're bind mounting in stuff that was compiled directly against the glibc libraries on the host. And that's kind of what you bring with you into the container. So this method is like almost assuredly going to break. That's basically the bottom line here. Is like not only is this like I mean I guess it is more portable than the other method.
And your application's still dependent on that specific MPI version, though.
Yeah, well, I compiled it on the host.
Yeah.
And then I copied it into the container, and then I copied the MPI into the container, and then I copied all the libraries into the container. And so you start to wonder, what's the point of the container? Why am I wasting all my time just copying all this stuff into this empty container just to say that I ran it inside of a container when I was done? You don't get anything out of it. So I don't think the bind model is actually, very widely used, and that's kind of the reason. But anyway, if I ran that, it would run and you'd see the same messages that I saw previously. I'm not going to waste time doing that because we are running out of time. I'm sorry, I'm so long-winded. All right, let's go to the fully containerized version. This is with Pimix, or PMI rather. Okay. In this example, we're making a few different changes. One of these is the definition file now. Instead of just creating this whole definition file from scratch, which would still be kind of a complicated endeavor, even though it would be easier because I don't have to match a particular version, we're going an even easier route, and we're just using SPAC. So SPAC is a really cool tool that we have not talked about a whole lot in this webinar, I don't think. But it's been around for a while. It is a package manager, which is kind of geared toward HPC, which tends to build everything from source, essentially, in a nutshell. And you can make these little spec files that you can use to install stuff. In this case, I'm installing a specific version of GMake along with OSU micro benchmarks. I don't think I'd actually have to install this for this container to work. But I'm also installing Open MPI. I'm specifying what fabrics I want it to use and what options I want it to be compiled with. And then I'm installing libfabric. So that's something that, hopefully we'll be able to talk to a little bit if I hurry up and get through this quickly. But here's the cool thing. You can use SPAC to build containers. And so, when you have all these parts down here, which actually specifies some details about the container that you want to build, you can use a command called SPAC containerize, and it will spit out for you a definition file. Now, in this case, I've got this definition file here that I created with the SPAC.yaml, and then I edited this definition file myself to add in this MPI hello world, which is kind of ugly. I probably could have figured out how to just do it all with the spec file, but just to be quick and dirty about it, I just went ahead and edited it myself. But so the point of all this is that once you get this together, you've got everything completely containerized. And I guess maybe what I should have pointed out in the spec.yaml, we're putting PSM2 support here in this libfabric. Oh, and PMI. I'm sorry. We have PMI support in OpenMPI. So what this allows us to do, I'm going to show you this command I'm about to run. And this is very similar to what one of our viewers was talking about earlier. We're just going to use srun. And when we use srun, we're going to pass this command that says, hey, use PMI2 for your MPI wire up. And then we're just going to tell it the number of tasks, number of nodes, and we're going to give it, once again, that Apptainer exec. And one of the cool things about this is this works regardless of whether or not you actually have MPI installed. So let me just go ahead and run it. So I'm just going to execute the command in kind of an ugly way.
Which, to be clear, is why this environment didn't have MPI installed, and why, in order to demonstrate otherwise, Dave had to jump through all those hoops to have a system-level MPI. We wanted to be able to show that this would run without any MPI system-wide.
Yeah, and in fact, I guess a quick and easy thing that I could do, if I open up a new shell, I mean, you guys saw me run those export commands. I guess if I open up a new shell, I'm not going to have that. It's not. I'm still going to have those environment variables set. But what I could do is,
I love how the shell is just dinging you like crazy.
Yeah.
What is that? What does that mean?
He's hitting tab a bunch.
Yeah, it's giving me the finger and saying, "Do it yourself."
That's awesome.
There we go. All right, I'll unset that. That should break things, right? Watch it will break things. It'll be really sad. Oh, see, it still runs. So now I just unset LD library path. So I effectively don't have MPI. I've got the MPI binaries still on my path, but if I actually tried to execute them, they would break, and because they don't have the libraries that they need anymore. And it still runs. And it's still, if we go up and we look, let me see if I can find it. Here it is. It's still using the high-speed interconnect. So it runs and it runs in a performant way. Cool. So, okay, I left us like 6 minutes. But I think we should talk. So that's kind of like the more modern way. This is portable now. You can take this container to your point, Rose, and as long as you've got Slurm, which is compiled with PMI, which is going to it's going to become more and more common, is already pretty common. You can take this to another place and you can just go ahead and run it without having any external MPI implementation. So that's the first problem. That's the wire up problem. Now let's talk briefly a little bit about the interconnect problem if there's time.
We have a few minutes for sure.
Cool. So I think let me set the problem up again. So I think one of the problems historically has been you've got this kernel module and you've got this set of libraries, and those have to match. But then on the other side of the libraries, you've got your MPI implementation, which was compiled directly against them, and those have to match. And so now you've got this thing that's got to match from outside the container all the way through or from inside the container all the way through back to the outside of the container. And so now it's not portable anymore. Enter libfabric.
Yeah, are you throwing to me now, Dave?
Yeah.
Okay. So, libfabric, there's a couple things going on here. One is that it appears, and we're still testing this, but it appears that libfabric is portable between different kernels. So Dave and I were, before the webinar, just musing about whether this was true or not. Because we've seen, I think there was someone in, I think it was the Apptainer community that was having trouble because they'd backported the Rocky 9 kernel into a Rocky 8 system to get additional hardware support, and it broke InfiniBand or something like that. And
Shocker.
yeah, and that was because there's, like Dave just said, a user space portion that was still there from the Rocky 8 side, but now the kernel side was Rocky 9. So far, it appears like libfabric is portable across that. And my anecdote right now is all this benchmarking that I'm running, without thinking about it, I was running a Rocky 9 container on my Rocky 8 hosts, and I didn't even notice. So we want to do the full matrix of that and do some performance testing of running a Rocky 8 container on a Rocky 8 host, and then both sides of 8 on 9 and 9 on 8. And then 9 on 9, just to test all of that and make sure that there's no weird performance gotchas or that one of those permutations doesn't create a problem. But so far, it's looking good. The other is that historically you've built an MPI against a given fabric, and so you would think that you need to build your MPI on your system to build it against the high performance fabric that you have. And so that might make you not want to all have it in a container that you downloaded from the internet or something. So like historically, for example, you might build OpenMPI, and when you say fabrics equals, you would say fabrics equals PSM2 or OPX, the new OmniPath one, or maybe you say verbs or IB or whatever the thing would be to build native InfiniBand support. Well, now one of the fabrics that OpenMPI supports, and in fact all of the major open source implementations now support, is libfabric. In fact, I think MPitch and MVAPitch just only support libfabric now. So that's where you have your one-to-one support. Those are built against libfabric, and you must have libfabric. But libfabric itself is a multiplexing library, and if you saw in that spec definition that Dave had, the fabrics that it supports is not just PSM2, but a list of fabrics that you're building in support for. So you can just do traditional network sockets, you can do TCP or UDP, you can do verbs, which I think is still the preferred kind of interconnect for InfiniBand, Mellanox InfiniBand, or PSM2 or OPX, which is what I've been using more recently. And an EFA one. That we're not building here for some reason, and the last time this came up I was trying to do it in the middle of a webinar and I still haven't gone back and done it. But you should be able to build this one container with this one libfabric build in it that supports all of these fabrics, that you can just take it from one to the next and it would just be portable across them. So that's the goal. That's what we're working towards, and so far it's going well, but we're trying to be cautious and actually go and test all of our assumptions about performance. So that's what we're doing right now. If you've done any kind of comparative benchmarking before, it quickly turns into a nightmare of permutations and matrix comparisons. So my hope is to have a new blog post out about that in the coming weeks, where we'll at least report what we've observed. From a startup standpoint and actually support getting this to run on things, it's going well. We just want to make sure that you're getting the best and optimal performance that you can with the software you're trying to run. So that is our future work.
Yeah, so just to kind of sum that up, I think libfabric is like an abstraction layer that just goes out and says, what do you got? Give me what you got and I'll run it. Yep. And in that way, it's kind of cool because it's kind of like CUDA, the way that CUDA works with the NVIDIA driver. There's not this tight correspondence anymore between the driver and also the hardware. You can kind of go out and say, I can run on multiple different things. Tell me what you got, and I'll tell you how I ought to run it. So that's encouraging.
It's great, and I really appreciate the work that you guys have done. Jonathan, I know you spent a lot of time on this too. Looking forward to the next installment of where we're going with this. It's exciting.
Yes, as am I.
Thank you guys very much.
It just keeps growing without bound, so I'm looking forward to actually having a conclusion to it.
Will there ever actually be a finished conclusion?
I don't know.
Sorry, we'll Jonathan. It just is going to keep expanding, just like the whole universe, right? It just keeps going.
We just keep. The more answers we find, the more questions we have, and it's both a good and a bad thing.
Yeah, it keeps it fun for sure. Well, thank you guys. Thank you everyone who showed up. Thanks for the questions and the comments and your attention. We are more than happy. If you are not watching this not live, go ahead and leave a comment. Feel free to go to our website, ciq.com, reach out to us. We will all get the emails. We will respond to you. We're very excited about all the things that we are creating and working on and ways that we can support you. And like as a smaller company, which is really cool, we have the opportunity to be very responsive to our customers and what it is that you guys are doing and needing. And that's part of one of the joys of like their never ending questions and things to solve. So we're very happy to do that. So make sure that you like and subscribe, share this with your friends, leave any suggestions on future things that you want to know more about. And we are so glad that you were here. Thanks, guys, for being here. See you next time.
And go see Dave at Stanford on Monday.
Yep.
Monday, that's right. Yeah, it's not 4,
Monday.
It's 2. It's at like 2 or 2:30. Yeah. So the link should
2
be
to 4.
in there. 2 to 4. Yeah. It's all over.
Go
say hi. See Dave. Ask questions.
Cool. Awesome. Thanks, guys.
Thanks, everyone.
Bye.
Appreciate it.